Hello students, a very good morning to all of you. Welcome back to LNT College Multimedia Studio. Today our lecture is focused on metal complexes and uh, nature of metals and ligands. How the metal and ligands form complexes. By using the Werner's theory, we can conclude that each and every metal complexes consisted of two type of valences, that is actually primary valences and secondary valences. So in the chemical adduct that was used by the Werners, that is COCl3 into 6NH3, that was actually so this chemical adduct was designated as CONH3 So here metal is cobalt and which bears +3 oxidation state, right? So the primary valency of this complex is +3 and the number of ligands that are directly bonded to this cobalt 3 plus is 6. So coordination number is 6 and oxidation number +3. So this is primary valency and this is secondary valency. So each metal complexes have two type of valencies. This is primary valency and secondary valency. Secondary valency is related to geometry of the complex, right? Geometry of the complex. While primary valency related to electronic structure of the metal, right? So metal play a very important role because of the following regions. So the region behind that the metal forms complexes because metal, especially transition metals, or you can say simply D metals like scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So these are the 3D series. 3D series, right? 3D series. So all of these metals have vacant d orbitals, right? So vacant d orbitals. Vacant d orbitals. And because of vacancy of these d orbitals, all these metal acts as a Lewis acid, right? So they are called Lewis acid. Lewis acid means these metals are electron deficient, right? So this is actually electron deficient. Electron deficiency means they have tendency to accept a pair of electrons from electron rich species, that is called ligand. So electron deficient species are called Lewis acid. As you know that the complex formation is because of reaction between Lewis acid and Lewis base. So Lewis acid plus Lewis base, right? After the reaction they form complex compound, right? So Lewis acid, greater is the charge on the metal, or simply you can say if the oxidation number is very very high of the metals, so they have tendency to easily accept a pair of electrons. So larger the Lewis acidity, greater will be tendency to form the complexes with the ligands. So suppose we have one example, that is scandium, so which have atomic number 21. So its electronic configuration 1s2, 2s2, 2p, 6, 3s2, 3p, 6, and 4s2, 3d, 1, 2 to 4. So this is actually 3s2, 3p6. Actually, they are fully filled. 4s2 fully filled. 3d partially filled, right? So it is partially filled, and each d subcell have 5 d orbitals. So it means 1, 2, 3, 4, 5. So this is 5 d orbitals, 1 electrons, right? And the valence shell of this metal, that is 4s, because 4p, 4d, 4f they are vacant, and 3d because 3s, 3p, 3d. So two cells are actually incomplete. So it has uh, valence shell, two valence cell, that is one for corresponding to principal quantum number 3 and second one correspond to principal quantum number 4. So what happens here? Here one orbitals, this is second orbital, this is third, this is fourth. 4 orbitals are vacant. So they can accept a pair of actually one pair by ligand. Since each orbital contains a pair of electrons, right? So all the metals undergo hybridization to give a particular geometry or direct attachment or directional to give a geometry, right? So what is it? So that is, suppose we have a complex SCH2O whole 6, right? So this is you can simply say 3 plus. So scandium in the plus 3 state, it forms a complex like that. So primary valency is plus 3 and secondary valency is plus 6, and the geometry corresponding to this complex ion is octahedral. So depending on the number of ligands which are directly bonded to the metal or metal ions, gives us idea about the geometry of the complexes. Coordination number 2, the geometry is linear. It means ligands can linearly arranged around the metal or metal ions. If coordination number 3, then there may be trigonal planar geometry. If coordination number 4, tetrahedral or square planar. If coordination number 5, that means square pyramidal. Square pyramidal. Coordination number 6, octahedral right? And coordination number 7, pentagonal bipyramidal. Pentagonal bipyramidal. So most of the metals actually they forms uh, 2 to 12 coordination number, and they have different geometries, and the geometries actually come from because of the participation of the valence orbitals through the hybridization, and they have deficient or vacant orbitals actually that can accept a pair of electrons from the ligands. So the coordination number gives the idea of the geometry of the metal complex, right? So we have metal complexes, metal complex. So transition series, or you can simply say 3D series, actually they have tendency to change their oxidation state, and because of the variation of the oxidation state, they can form a variety of complexes with different ligands, right? So different ligands will give different complexes with the same metal cation. Suppose if we talk about the iron, so iron possesses two type of valency, that is two type of oxidation number, Fe2 and Fe3. So the complexes formed through these two ions will have definitely different chemical characteristics, right? So CO2 plus and CO3 plus, right? So Mn2 plus, Mn plus 7. So transition series have variable oxidation states. So because of this, they have very good deficiency in the orbitals, and they can accommodate a pair of electrons. So and adjust the number of ligands around it to provides a suitable geometry, right? So like we have a, this is TiS2O ka whole 6 and 3 plus. So this is cationic complexes. Here oxidation number is plus 3, primary valency plus 3, and this primary valency is saturated with uh, oxidation number or coordination number, that is 6, right? So here 6 water molecule is arranged around this titanium 3 plus, give a octahedral geometry, right? Geometry. Titanium 3 plus means the electronic configuration of this metal cation is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, 3d2. Since oxidation number is plus 3, so 4s electron and 1d electron will be actually removed. So here 4s is fully vacant, and 3d and 4p, of course outer orbital is vacant. So 4s, that is 3d and 4p. So we need 6 hybrid orbitals to create octahedral geometry. So 1 s and 5 d orbitals and 4 p orbitals. So give a total 6 uh, hybrid orbitals. Hybrid orbitals, right? So here you can simply say this is 4s, and you can simply this is 4s, this is 4p, and you can also one, two, three, four, 5. So this is 3D. sp3d2, sp3d2, right? So the hybridization will take place like that. So to form 6 equal energy and proper symmetry to accommodate a pair of electrons from the ligand. So this is sp3d2. Okay, so they can accept one pair of electron. So 6 orbital means they can accommodate 12 electrons from ligand H2O, right? So C, that is titanium 3 plus, total 12 electrons accept, right? Because of the octahedral geometry, 6 water molecules can donate total 12 electrons in the 6 hybrid orbitals, which were formed through the hybridization of the valence shells and valence orbitals, right? So similarly, a variety of metals actually have been found to create a variety of complexes. Okay, so in the next lecture, we will try to focus on the nature of ligand in detail, because actually ligands, they are donor centers or donor groups. Okay, so that forms actually dative bond to metal cation or metal ions. So what are the natures of ligand? So that will be discussed in the next lecture. Okay, thank you.